Okay, so in the last class, I've just provided you a little introduction on the subject called principles of GPS. But in fact, when we talk about the broader subject or a broader category to which the GPS belongs to, obviously that category is called as space geodesy. So I've told you the meaning of geodesy is that when we study the shape and size of the earth, we take help from various tools and techniques, then we study the shape of earth. One figure is just on your screen. That's how the scientists look at the earth, and from different aspect. And when we do this such kind of a study from space, that means from space techniques or from various satellite orbits, when we do this kind of a study, this is called as space geodesy. So GPS and other equivalent uh, space based navigation satellite system, they are all part of GNSS. They are all part of so-called geodesy, space geodesy. I hope it is very clear to all of you. Is there any doubt in this statement? So once again, we are reading, or we are going one by one uh, inside this space geodesy. So space geodesy, then the one branch is called as GNSS. I've told you some examples of other branches also. That one is GNSS, another is VLBI, another is SLR, another is DORIS. So these are all type of space-based geodetic techniques, or they are also broadly categorized as space geodesy. So one part or one type of space geodesy is GNSS, which we are discussing here. Uh, this principle of GPS, the course, why it is titled as principles of GPS is because many times whenever we somebody asks that how do you locate your position through mobile, we simply use this word called GPS. We have this GPS in our mobile, isn't it? So just by conceptually maybe different, but users are more frequent with this term called GPS. Okay, so even although the Russian, which is GLONASS, Russian's GPS is GLONASS, isn't it? So the GLONASS is very less popular. Galileo is from European Space Agency. That is very less popular. I'm not saying about the scientific community, but in the general user or in the public, it is very less popular. The name GPS is very popular. Okay? Maybe because it's very short, or another thing is that it came early towards these two, GLONASS and so-called Galileo. Okay. Having said that, we have this space geodesy with us nowadays, and there is a huge potential in this domain. But in order to study that potential, we first need to know about the basics of the fundamental datums, isn't it? So the reason is very simple. Whenever you say what is we for what purpose we use GPS, isn't it? So when we say that we use GPS for providing the location or providing the coordinates of unknown point or something like that. So immediately it should hit your mind first that if we are talking about the location or coordinate of an unknown point, then it has to be referred through a proper datum or origin or coordinate system. Only then these coordinates or these location will have certain meaning, isn't it? If somebody says my house is 30 kilometer away from institute, I mean you are in a circle of 30 kilometers, isn't it? Your house can be anywhere until and unless you provide any other reference or benchmark or any information which required to locate your house within that 30-kilometer kind of boundary. So that is the so-called essence of understanding the so-called reference systems or datums which we potentially focus on. Anyways, Then this topic, which is also known as, I mean, in GPS, GNSS. In GNSS, generally, what we do, we try to study at the last about the other GNSS also, GLONASS and Galileo. Please remember this IRNSS, which we call it as the Indian Region Navigation Satellite System, which our country has right now. It is not part of GNSS because it is not global in nature. You must understand that GNSS is named as Global Navigation Satellite System. So this GNSS is a category for those satellite system where the orbit of the satellite system should cover the complete Earth, okay, complete globe, isn't it? But in the case of IRNSS, it is not so. That's why it is called as Indian Region Navigation Satellite System. In 1999, during Kargil War, because of some diplomatic condition, US has turned off the GPS for Indian region. So our soldiers had to, fight it, fight it out, some mechanism to locate their position in the unknown territory. After this event, this our government of India has worked towards first providing us Gagan, and then after this Gagan, this IRNSS segment was launched during Dr. Kiran Kumar, who was the ISRO chief at that time. So Gagan is something which is part of SBAS. SBAS is a different altogether augmentation system. It's a full form of SBAS is called as space-based augmentation system. That is critically identified as a technique by which a few satellites are launched into the orbit and they will provide the corrections to your receiver, so that if you are working in an unknown territory, you do not have any other processing environment. What you will do, you will take the facility of the SPAS in that territory. If it is India, you will take help from Gagan satellites. And then two satellites are there in the space and they will provide you the corrections so that you could correct your position with respect to the other sources, maybe atmospheric, orbital, or maybe any other uh, unwarranted error sources that are there. So you could correct yourself and you can have possibly reasonably good accuracy, okay, compared to the post process. Okay, so in this light, when we have this concept of GPS, we have to understand also at the same time the different aspect of the development, of historical evolution of your coordinate system, and why it is also important for you is that you should also look at the historical perspective of this GPS. So when you say GPS, so obviously the development and performance is one aspect, as well as the categories of application is so broad that you can think of anything and you will have GPS as a role to play in it. Okay, as part of geoinformatics profession, you cannot avoid GPS. Okay, if you are using satellite image processing, if you are using web GIS, radar, or any INSAR, SAR, whatever domain you think of, you cannot avoid application of GPS into finding out something scientific to your research. Okay, so obviously GPS made its debut in geodesy with very big announcement, and during the summer of 1982, and during the testing of the micrometer receiver developed by some scientists at MIT, they verified the GPS surveying accuracy of 1 to 2 parts per million of the station separation. So you could imagine in 1982, not in 2022, it is 40 years back, you have in 82, you will have 1 or 2 ppm. Ppm means parts per million of the distance separation. So that means it is 1 ppm. If the accuracy is 1 ppm, that means you multiply the 1 with the kilometer and you will get that much precision in the distance observation between 2 points. So that is the beauty of GPS, which people have observed in the early 80s. And obviously, that was some basic understanding of the GPS, which is there. But from geodetic aspect, I mean, we are geoinformatics professionals, so we have to look things into two aspects. One aspect is obviously the application domain. So certain applications require very less accuracy kind of application. So suppose you are moving on a lane in a road, so your accuracy requirement would be 2 to 5 meter would be decent to your work. But in certain domain of let's say terrain motion, or let's say crystal motion, or earthquake prediction, landslide investigations. So these are the certain domain where you need millimeter level kind of accuracy. So I hope you get this very straight, that you have two kind of application. One with meter level kind of accuracy, and then on the second you will have millimeter level kind of accuracy, isn't it? So these are the two requirements. So one is your the so-called millimeter level requirement, where you do not need very high precision observation or high precision instrument itself to provide you this millimeter level precision. But on the second case, you need very robust and very sophisticated geodetic quality receivers to provide you this millimeter level precision. Obviously, fundamentally also you need to think on the solution, how you are getting this precision, which is of millimeter level, how which part of observable we are looking into it. Okay, so it becomes increasingly important to focus on the definition of the reference frames. Okay, so obviously, as we are talking about the millimeter level accuracy from geodetic space techniques, our requirement to define the frame is also required. When I say reference frame, at this point you do not get into the terminology very much. You just think that we are talking about the datum, to be precise. So let's say if you are measuring something from a table, let's say, okay, or from a surface, from an undulated surface, if you're measuring something, then obviously the undulated surface has to be defined first very precisely. Otherwise, what will happen? Any measurements from that undulated surface would be erroneous. Your observations are prone to errors, isn't it? And so, what you need that surface or undulated surface from where you are taking the measurement. It has to be precise. Similarly, in our domain, we talk about the reference systems, reference frame, the shape and size of Earth, the figure of Earth. They has to be precise. If they are precise, only then any measurements which are being taken with the help of these coordinate system or shape or the Earth surface, they will be considered as precise. Okay, so that's why this statement is very important, that it becomes increasingly important to focus on the definition of reference frame as the accuracy of geodetic space techniques increases. So we need to define first the so-called our datums, our reference frames. Okay, I'm not changing the screens right now, so do not get confused that whether I'm speaking with certain content or not. I'm just speaking on a layman terms, the understanding of the topic. Because if you get the essence of the content, then it will be easy for you to follow books, reference papers, as well as the slides. Okay, so there are three types of frames which are we are more concerned with, we are more focused with. One is called as a frame which is earth fixed. That means you visualize your earth, and we are thinking of a reference frame which is earth fixed. Then since your satellites are in the space at 20,000 kilometer away from Earth's surface, you look at various kind of the so-called what should I say, the objects in the space apart from your satellite orbits. So that space is also called as inertial space, or called as a celestial space. Why? Because if you have this capability to visualize, you move out this the so-called in the space, and then you'll see various objects like moon and other planets, they look stationary to you. They are not moving anywhere. Obviously, that is the visualization from which you could see, imagine the Earth's surface from the space. So, since it involves your visualization from that domain also, you will have this called space fixed frame, and then obviously the geodetic datum. So the third component, which is geodetic datum, is the datum which our local space or geodetic agency establishes. So in India, this geodetic datum is established by a Survey of India. So I hope you have heard this term, Survey of India, many a times. So this geodetic datum is established by Survey of India. That geodetic datum consists of two information. One is horizontal datum, and another is vertical datum. Mostly and more prominently, we are talking about the vertical datums when we talk about the geodetic datum. Okay, so of course we need to able to transform between these frames, and this the contribution which is coming from the scientist, or the requirements coming from scientist for a clear definition of coordinate, as well as to fully explore, the phenomenal increase in the accuracy of geospatial or geodetic space techniques. uh, uh, the definition and maintenance of these frames which I'm talking, earth frame, earth fixed frame, space fixed frames, and geodetic datum, they are critically important. So as I've told you, for GPS, earth fixed frame will have a little clear definition. For space fixed frame, we'll have a clear definition. And obviously for geodetic datum, we have definition by country specific zone. So suppose for India, Survey of India will provide the definition of that datum. For America, US, NGS, National Geodetic Survey, they will provide this definition, and so on. So obviously our objective is to focus on first the frames which is earth fixed and is space fixed. Obviously we'll look into this figure. uh, uh, so this figure which you are looking at your screen right now, this is called as geoid of Western Hemisphere. So it is more popularly, because this content is from Professor E. Carius from Purdue University. So they have more predominantly they have taken this figure for Western Hemisphere, and at there this is called as geoid. Well, we all know with your last year background what is geoid. Geoid is nothing but the so-called uh, point of equipotentials, surface of equipotentials, from which we measure the height in a local territory. Okay. So with this, we are changing slide to your, and in fact, I don't know whether my cursor is moving at this place. Can you see my cursor? Hello,
No,
Yes,
sir.
sir.
Yes, sir. Yes, sir.
It's
is it
in the
visible?
left side,
So you
bottom left
see
side.
this. Hello, yeah, left bottom. You see this the name of the content which is written as GPS geodesy. So this very closely correlated the terms, how the classes and how the topics, or how the courses are assigned at outside world. So this GPS geodesy is the topic class name, sorry, course name, which through which we get this content. I've taken the permissions acknowledgement from professor for using his content for classroom lectures. Okay, so when we discuss this, the shape of Earth, we have a very clear evolution from looking at this understanding of the shape. So in before 3000 BC, it was called or named as oyster. Many a times you would have seen the oyster kind of you know uh, in coastal regions. Um, so they've defined the shape of our Mother Nature Earth as oyster. Then this Pythagore came between 582 to 507 BC, and they speculative consideration based on aesthetics, based on, see, at present it is 2022. Okay, you have so many things on your in terms of gadgets. You can think of anything, you just Google it. But think of this tenure, which is we are talking here, 582 BC. They do not have anything such like Google or YouTube or your mobile phones. Just look at their imagination, how they conceptualize that, how the earth looks like to them. Okay, so this speculative consideration based on aesthetics, based on understanding of their literature, their own culture heritage, they found that it looked like a sphere. Okay, they look like a sphere, and number 10 considered perfect. Perfect world would consist of 10 planetary bodies of spherical form. This is their culture. From there they identified that, okay, if we are living in this world which has to be perfect, it should be consist of some 10 uh, planetary bodies of spherical form. And it was he was first to suggest that earth rotated in a circular motion around the sun. So just think that with the imagination as well as with the daily events, that and when you are having a good morning, when you have a good afternoon and good evening, based on that he understood that we are moving around earth, around the sun, and that's how it concluded the Pythagoras. Then the Aristotle come in 14th century BC, and with this, all heavy bodies tend to fall towards the center and seek the lowest plane in the process. Thus, they are eventually pressed into spherical ball. And observations, and they looked at ships at sea. Superstructure is the last seen going away from land. You just visualize for this, for kind of Burj Khalifa kind of thing, that these are the superstructures. The changes in observables, star going north and south, earth cast round shadows during lunar eclipses. So with these conceptual understanding, these two gentlemen, they decided that they have given initial assumptions that your earth is indeed a sphere. Okay, obviously these are the only assumptions. Then without any without any physical observation, that means the observations which is ships at sea, superstructure is last seen, but they are just by visual observation. There's nothing, measurements have actually been taken. So with this little background, there's one gentleman which is very popular in our geodesy, is called as Eratosthenes. Eratosthenes in 275 to 195 BC, which is head librarian in Alexandria, Egypt. He got a little idea. Okay, why not? What we do, we take certain understanding. So if it is called in jokingly in our domain, it is called as, if Eratosthenes hasn't under the well or inside the well, we couldn't have observed our Earth is not a sphere. So what he has done, he has he two wells, one in Scene and another is Alexandria. That there are two wells. So what he found is that sun rays vertical at Scene at noon on summer day, but shadow on well side in Alexandria. So it means the sun rays are vertical towards inside the well in Scene, but little inclined, and that's why they are providing certain shadow on well side in Alexandria. Knowing the distance between these two, I'm just observing you. This is the Scene, this is the well in the Scene, and this is the well in the Alexandria. Okay, just give me a moment. I'm just I'll
Okay, so that we were discussing about the development at the scene as well as Alexandria. So what is the distance between these two places, which is seen in Alexandria? It is 10 camel days. Maybe the camel days is their way of having this the measurement scale. So it is 500 stadia, and 500 stadia, when you multiply it by 185, it convert to some length. An Earth radius, which we know is this. Let me computed is 7364650 meter, and with this circumference 2 pi r, we they multiplied that, it is 46250 meter, uh, and which is which exactly their understanding is that it was 50 40030 meter in reality. So they accounted that there is certain error in the measurement of the complete periphery. So it is it is understood, or it is decided based on this observation that the both places called Seen and Alexandria are not on exactly the same meridian. What is meridian? So from North Pole, just by physical, you just take the globe, you hold the globe from two places called North Pole and South Pole, and then you join the lines between North Pole and South Pole. So the moment you join lines, so this first line which you draw from North Pole to South Pole on a globe, if you have a globe on your hand, just hold it from the 2 points, North Pole and South Pole, and you just join a line between the two. That is called as meridian. Okay. So if the 2 points are on the same meridian, okay, and if you have a different line which is joining the uh, north and south, that becomes two places which are on different meridians. So that's what it is written as, Seen and Alexandria not on the same meridian. So this is spherical Earth models often used for short range navigation, which is WAR DME. WAR DME is just a name convention, short range navigation for global distance approximation in seismology, plate tectonics, etc. And it works with this 40-kilometer difference for polar radius. So, anyways, that was the earlier developments, but our the father of geodesy has been named with this concept of this simple experiment which is conducted at in its era. Okay, so measuring latitude and longitude. So you have latitudes, which is nothing but the zenith angles of the sun at noon, accounting for declination from a table, and then the corollary length of a degree from zenith angle to distant star. The latitudes more difficult than latitude. These are we are talking about the previous concept based on which we are measuring these latitude and longitudes. The more difficult than latitude, use Earth rotations, local time minus time at reference time. This becomes the longitude. The local time is maximum sun elevation at noon. Time at reference site need accurate clocks. So these are the initial approximation for which people have decided to move forward with a little more precise information about the Earth's surface. So this decision that your Earth is not a sphere, in fact, it is taken in by uh, Jean Picard during 1669, where measured the meridian arc from north of Paris to Eminence using triangulation and astronomic latitude at ends, and it continued north to Dunkerque and south of Collioure by Philippe de Lahire and Jacques. So there is a proper what was a French expedition has been conducted in 16th century, which we popularly call that, for taking the two measurements, 1 degree measurement of length at equator and 1 degree measurement of the arc at poles. So you could see it is written as LE, which is length at equator for 1 degree, and length at poles for same 1 degree. So it has been found out that the distance are not same at two places, but it has to be same. That means this gives little indication that something is wrong in terms of the shape and size of the Earth, because if your so-called uh, the length at equator and poles are same, then you can consider your Earth surface as spherical in nature. But these evidences that 1 degree length of at pole and 1 degree length at equator are not the same, that gives little hint that something is wrong with this spherical understanding or spherical assumptions. Okay. So spherical tangent to the pole has a smaller radius than at equator. Therefore, Earth is egg-shaped or prolate ellipsoid. Prolate spheroid that has been interpreted with this French expedition. There is a lot more content is available, but in general, it is for your understanding that how this evolution of spherical to ellipsoid has taken place. It is purely based on these expedition, these physical measurement. It is not based on your assumptions. Okay. Okay. Then the Newton came up with this little more detailed concept um, that the theoretical consideration is that we do not have only mass in our Earth's surface. We have the fluid also. So it is a rotating body with mass and fluid. So we have two things. So in your at your home also you can experiment a bit. You fill a body, fill a water tub or a balloon or something like that, and you fill inside it. You put certain mass apart from this fluid, and you try to see, and you try to rotate it out. Then you will see that it is not the movement is creating a little uh, tension at the equator, and this because of this people try to estimate the flattening option, because if you have a fluid as well as mass in a body and you are rotating, so the moment you rotate, the mass tends to flow out from this axis, and because of which what we'll have, we will have this so-called this elliptical consideration comes into the picture, and then people observe this flattening, and found Newton found this flattening is 1 by 230, which is represented by 1 by f for ellipsoid, which in reality it found that as 1 by 298. So French Academy of Sciences orders a test. Okay, two expedition for measuring the length of one meridian. One at 1736 Laponia and 1743 at Peru. So they found that 1 degree is so-called longer in Laponia than Peru. So a spherical tangent to the pole has a larger radius than at equator. Therefore, the poles are flattened. So it looked like that something is pressed from the top and expanded at the bottom. Expanded at the equator. So with this understanding, this first definition of the meter, which is 10 millionth part of a quarter of the circumference of an Earth meridian, this was defined as the definition of meter. 10th 10 millionth part of a quarter of the circumference of an Earth's meridian. These expedition proved that the length at equator and length at pole, they looked at this with little concept that what if, so you could think in this figure, what is interesting in this figure is the circles, different circles which you see or observe. So with this length of LP, which is 1 degree, it to have this particular arc, it considered as this bigger body should reflect the so-called the shape of Earth. But with respect to this little 1 degree arc here at the equator, it reflects that the body should something like blue of nature. At this place, it looked like with this radius and everything, it looked like this kind of body. And with this understanding, it looked like as a green kind of body should represent the Earth. But in fact, if you consider the ellipsoidal understanding, then this would become the foci, and then based on this and considering the flattening, this actual ellipsoidal section of Earth looks as that this should be the your Earth's body. So not the red, not the blue. In fact, this black boundary is your Earth surface or ellipsoidal section of the Earth. How do you see the section? When you cut from top to bottom to get a section. So this is the section which is flattened at poles and bulging at equator. Okay. With this understanding that your Earth surface is not a sphere, it is ellipsoid, then obviously you have to mathematically represent it by the definitions, by certain parameterization of the Earth's surface. So the shape of the Earth is mathematically represented as an ellipsoid defined by semi-major axis, semi-minor axis, and flattening. Please remember the prolate word comes when you rotate the body with respect to the vertical axis. Okay, so this prolate ellipsoid which you are uh, looking at this is with semi-major axis A, semi-minor axis B, and the flattening. Okay. So this flattening is nothing but A minus B upon A, or eccentricity also is another way of representing the the case of ellipsoid. So you have a sphere, you have ellipsoid, and they are represented here in terms of comparison. So comparison between W is 80 for ellipsoid and a sphere of identical volume. So if you do not consider this bulging, rotation, mass, and fluid or everything, then how this Earth would look like with a similar or identical volume, it would look like as a sphere. But identically, it is not the case. Your Earth is rotating. It is rotating with mass as well as the fluid. So just take a look at this figure, and if you have any query, you can ask. As part of geoinformatics professional, it is expected that you should have little understanding how this shape of Earth has evolved over the years. Because what happens really, if you do not have this understanding how this has evolved over the years, how this rotation is coming into the picture, what exactly is the effect of these rotation on the surface of Earth, then probably you will miss certain what should I say, the conceptual understanding of the satellite motion around Earth, the various forces acting over the satellite, the orbital computations. So, I mean, it is a series of questions or query that would be put up, and that you need to answer, or also required to, for you to prepare your concept building in the topic. So that it is important that you go through with the content. I'll share few content also about the evolution, which is written in the document just by layman language. You just read that beautiful story, and you will feel very connected to the content. Just a moment.
Okay. So coordinates on the ellipsoidal Earth. So you just think that you know the given that the shape of Earth is close to an ellipsoid, it is convenient to define a position by its latitude, longitude, and height. So let's say you have a point on the surface of Earth or above the surface of Earth, which is located as P. What you want? You want that coordinate P is defined by three values like X and Y and Z. So obviously, you need to first think of how this X and Y and Z would be defined, the axes, because that is very much important. If you understand this geodesy, then the definition of this coordinate. So before having the value, you must know how the three axes have been defined, how the planes have been defined, how the meridians have been defined, and then you probably would compute the 3D coordinates. Okay. So anyway, just look at this point P. What has happened? You drop a normal from that point P to that will intersect this ellipsoidal surface where you have this 90-degree kind of sign. From that surface to that point P, you will have a height h, which is called as ellipsoidal height. Then this normal is intersecting at equator. The moment it is intersecting at equator, okay, you take first measurement from that equator towards that so-called that line that becomes phi. That is latitude. But in order to find out the longitude, what do you need? You need a reference meridian. So the prime meridian or the prime meridian, which is also called a 0-degree longitude line, is the origin for longitude, and the equator is the origin for the latitude. So your prime meridian. Now you must have heard, in fact, I guess, Greenwich meridian. How many of you have heard this term called Greenwich meridian? बताइए. बताइए वैली शेट्टी, आप बताइए. Hello, am I audible?
Yes, sir.
Sir,
हाँ बताइए. Have you heard this Greenwich? Because I guess it is very much popular among everyone. The short form.
The prime meridian passes through Greenwich, UK. A place.
Who is speaking? Who is speaking?
Sir Arun. Arun.
Arun. Yes, you are very right. That 0-degree.
Sir, actually, the Royal Observatory of England, which is located at the Greenwich place, the meridian crossing from that Royal Observatory, that is taken as reference point as a prime meridian.
वैली शेट्टी, आप बताइए.
sir,
हाँ बोलिए. I'm 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 not am I audible to you? I think your voice is not coming. Your voice is not coming, very Shetty. Hello. Hello.
So both of you have spoken right that it is Greenwich town, in fact, which is located in UK, from where the 0 degree longitude line is passing. So that's true, and I'm very happy that at least a few of you are aware of it. So that 0 degree longitude, okay, the 0 degree longitude is the line which is this line, okay, which is this line, which is called as reference meridian. From there, in anti-clockwise direction, you go from that particular line to the so-called the line which is intersected, the normal which is intersected at equator to that point, and that line joining from that particular point to origin, that becomes the geodetic longitude, angle between the reference plane and a plane passing through the point, both plane being perpendicular to equatorial plane. So just like you have an apple, use your knife from the top of apple, you cut the knife between uh, top of that particular apple point and to the middle, you take a reference meridian line. Then from the again top, you again chop towards that point which you highlight over the apple, and that point from the midway, if you intersect and take it out, that little piece of, you know, the figure is at bottom. At the middle, you would look at the so-called longitude, and that vertical which you have drawn from that particular point P to the equator, that would be so-called is latitude, and the height, which is geodetic height. So with this little concept, is there any doubt in this? If any one of you have any doubt, you can ask. Otherwise, what will happen? Yes. Anyone?
Sir, this phi angle, how, from where it is being projected? Because the phi dash is being projected from the center of the earth to that point.
We are not talking about phi dash now. We are only talking about the phi. Phi is projected from point P, intersect the surface at this the ellipsoidal surface, from where you measure the height, and then it again go down and it will touch the equator. Okay, it will touch the equator. The moment it touches the equator, you get a point. You will join that point with the origin. That line is indicated as at this in this particular figure. The line, the phi has phi has measured from the point which is just intersected the equator. You will see a line from origin towards that point which where it has it intersected. Is it visible to you?
Yes, sir.
What is your doubt?
Sir, my doubt was how from point P to the line where phi angle is being represented, how this line has been projected to that point. The line at which it is being projected, that is connecting from center of the earth to the equator, that is okay, sir. But how this line is being projected from that point to that place, phi angle?
Now it is clear?
Sir, not completely, sir.
बताओ.
मतलब कि ये सर यही लाइन, मतलब कि हम क्या ये जो पॉइंट पी से जो ये ड्रॉप हो रहा है सर, ये लाइन जो फाइव एंगल बना रहा है नीचे लाइन में, क्या ये परपेंडिकुलर टू द सरफेस है?
Perpendicular to the surface, yes.
सर आपकी आवाज क्रैश कर रही है.
Yeah, it is perpendicular to the surface.
अच्छा अच्छा, okay, then okay sir, got it.
If that perpendicular, okay, please mind it,
if that perpendicular has your just think in that direction. What if your surface or earth is an ellipsoid, sorry, is your if is spheroid or a sphere, what will happen? Any normal on that surface, where it will meet?
Center.
Center. The second case is only possible if your assumptions of your so-called what should I say, the earth surface is spherical, then this geocentric latitude kind of phi dash would be possible. Otherwise, we generally work with this prior concept of geodetic latitude, longitude, and height. This figure you should draw in your notebook, because this figure is very, because in various interviews also, uh, interviewers generally ask, okay, draw me, how do you define latitude, longitude, and height? Because that decides how, where you are dropping that normal, that decides your understanding. Okay. Moving ahead, now just think in that direction, that now you have defined your earth surface, but still you have not decided the axes of for Cartesian coordinate system, which is x, y, and z. So for that, this earth-centered, earth-fixed kind of reference simple coordinate system is we actually look for. Now, why it is earth-centered and earth-fixed? Why not earth-centered simply, or why not earth-fixed only? The reason is very simple. Suppose you have a GPS and you are moving with a GPS on Allahabad, let's say, or Prayagraj. What will have? You will have the values of coordinates of different points, isn't it? If your reference system is not of the nature that it centered at Earth, centered or fixed with Earth, what will happen? The coordinate will change immediately the next day. Then coordinate will change immediately next day. And at the same time, what will happen? Your coordinates which you are getting in India would might be reflected the same in the US. So this will create a lot of chaos. So what you want? You want your frame. Let's say you have a globe. You want to weld this XYZ frame from inside. So what will happen? The moment Z come out from the globe, you weld it. The moment Y come out from the globe, you weld it. The moment X come out from that globe, you weld it. What will happen? This XYZ frame is fixed with Earth surface. Now, when you rotate, this frame will rotate. And if XYZ and origin is fixed, what will happen? If you take any point on the surface of Earth near to your workplace, that value will not drastically change next day. Obviously, there would be some changes in the decimal place or centimeter place, sorry, millimeter place, but it will not be changed drastically, just I was telling earlier. Are you getting this concept or not? So the simple coordinate system is ECF. Why? Because it would perfectly fit for GPS application. The simple coordinate system is ECF, which is origin, center of mass of Earth. The three right-handed orthogonal axes X, Y, Z. Units are in meters. The Z-axis coincides with Earth rotation axis. The XY plane coincides with the equatorial plane. The XZ plane contains the Earth's rotation axis and the prime meridian. So it's very simple. The Z-axis coincides with Earth rotation axis. The XY plane coincides with the equatorial plane. The XZ plane contains the Earth rotation axis and the prime meridian. Now just think of this concept. If you have any query, just let me know. Alok, बताइए, is there any problem in this figure which you are looking?
No, sir. अभी तक तो नहीं है।
I don't see Rahul in the class. Is Rahul not attending the classes? Sumit?
He is leaving, sir. He is leaving the MTech.
Oh. So this Earth-centered, Earth-fixed frame. Now you must popularly remember the three axes, how they are defined, because we will be placing little deviation in the conventions. Why? Because to make sure that we have a very solid fundamentals about the Earth fixed and Earth centered reference frame. So the simplest coordinate system which we are talking about, ECF, there are 2-3 problems. Now I'm discussing about the problem so that when I took over the deviations in the definition, you probably understand everything. Now the first deviation is that the z-axis, which we written here as it coincides with the Earth rotation axis. That this Earth rotation axis would not be instantaneous rotation axis. That means at any instant you would not be having any the so-called axis which is constant. It is an averaged value of that Earth rotation axis which would be decided to coincide. Okay, that is first thing. Second thing is this XY plane is coinciding with an equatorial plane. That is fine. The XZ again, it will contain the averaged rotation axis and the prime meridian. So the problem is with the Z axis. Why? The problem is that we will discuss during polar motion when we discuss about the polar motion. But at present, you just think that this Earth rotation axis is not instantaneous Earth rotation. Instantaneous means you look at Earth right now from the space and there is a vector coming out from the North Pole. That would be the Earth instantaneous rotation axis. But we are not focusing on that instantaneous rotation axis. Instead, we are locating at the averaged value of previous multiple years of data of rotation axis, and then an averaged rotation axis would come out, and that we are coinciding with the z-axis, that axis. Okay, please focus on this part, because why it is important, because when you choose z-axis as instantaneous z-axis or rotation axis, the coordinate terminology is called as instantaneous terrestrial coordinate system. Instantaneous means for a particular instant it is applicable, not for all. Okay, so that's why we are providing little deviation.
And then the two coordinate, which is one is the latitude, longitude, and height for a same point, which is represented as XYZ in ECF, they can be transformed to each other. Okay, they can be transformed to each other. Okay, you understand this particular deviation. I'm just focusing on the basic definition right now, because what will happen later on, we have advanced coordinate system, but that will only have a little deviations from this basic definition. If you understand this definition, the advanced definition you will probably pick up very much clearly. At present, for the simplest coordinate system, had we not have very complex earth system right now, what will happen? We will work with the simple coordinate system. But since our coordinate, our earth is rotating in this space, and it is affected with a lot of forces, and we cannot imagine, we have countless forces that are acting over the earth surface, or earth on from its space, solar radiation pressure, gravitational attraction from various nearby the so-called planets. So with these little deviations in the basic assumption, which I mean that we are having this various forces acting over it, though that coordinate rotation axis is not the same every time. It changes very frequently throughout a day. But for defining a coordinate system, you can only take the assumptions, isn't it? So that assumptions we are highlighting here, but at the same time I'm telling you that these are only the simplest definition. They will work anytime for your understanding purpose, but later on, at present scenario, present requirement, we will be deviating a little more in the definition. For where we are deviating in the rotation axis definition, we will be deviating little in the prime meridian definition, we will be deviating little with the x definition, so that you need to understand. But at present, we are working with the simplest coordinate system, which we call it as ECEF. Okay. Now the ECEF, the same point can be represented XYZ in ECF, an ellipsoidal coordinate lambda phi h, but they can be converted. Converted in the sense, suppose you get latitude, longitude, height while scrolling down through Google Earth, you will get the latitude, longitude, and height. You can convert it. You can convert it to ECF XYZ, as well as you can, if you have xyz, you can reconvert to lambda phi h. So both two coordinate conversion will be discussed in your first laboratory, that is on Friday. We will discuss these conversion conceptual understanding. First you will be explained these conversion, and then the MATLAB code which you have to prepare for smoothly conduct the conversion between ECF to ellipsoidal, ellipsoidal to ECF, that you will do. Okay, that only required your understanding of the subject so far, and it probably you'll all will do very carefully, no issues, because all equations are available. You just simply have to code it out. Okay. Then the topocentric system or datum, that's what I'm telling you. In the initial discussion, I've told you, na, you have earth fixed system, you will have space fixed system, and then you have datum. So this is your datum. The datum which is provided by Survey of India. Now let me just tell you, suppose you have to, as a geoinformatics professional, you have to work for a topographical mapping in nearby area. So probably you are not aware, but many a times the surveyors, they start with Survey of India points. They start their survey from Survey of India points, from those benchmarks which they have given. They are providing, they are working with those Survey of India datums, and They start their survey from that point. So datum is something which is provided or given by local survey agency. In India, it is Survey of India. So topocentric system, which is coordinates, can also be referring to a local topocentric datum where you have origin which can be any place on the surface of Earth, three orthogonal axes, up, U for vertical, point upwards, N for north in the local horizontal plane and points towards the geographic north, E for east in the local horizontal plane and points to geographic east. That system is a left-handed system, and the units in this system are reflected in meters. Okay, so the conversion, the same point which I am telling you in the previous what should I say, the previous slide, I was talking that same point XYZ can be transformed from XYZ to latitude, longitude, height. The same point, if it is having latitude, longitude, height, can be converted to XYZ. Now we are adding the third component, the same point, the XYZ and the lambda phi h can be given value in local coordinate system also, that is NENU. Now suppose you are establishing a point with GPS, let's say. For example, let me tell you some very field practices very clearly. So let's say you are establishing a GCP. GCP means ground control points on the surface of Earth. What will happen? You will go with your GPS and you will place your GPS over that point. You will get a value, isn't it? You will get a point. That point is latitude, longitude, and ellipsoidal height. But for local survey work, you cannot simply work with ellipsoidal height. You need orthometric height. So you need to convert this using certain projection system, which is UTM-44. Let's say if we're working in Prayagraj, 44N, then you will use this in your field software as well as in your scientific software, processing software, and well, you will convert this data with that 44 UTM zone, and you will get this northing, easting, and up component in your field software. You understand this part? So from GPS, you will get global coordinates, which are either in Earth-centered Earth fixed system or in the ellipsoidal system. But for local level work, you cannot work with global data. You have to convert the global to local. How do you convert it? Either you have this such kind of matrices which you can play it out. You have this data either in you either have this data, and this NEU can be given with the help of this understanding of latitude, longitude. Okay, just take a brief moment and see at this slide, uh, and I'll ask questions to few of you. Okay, so the conversion which is mentioned here is very simple. It takes into the input from lambda and phi, and it converts with respect to the origin which you are having on field. So suppose you have a origin and you have a separate point. So 2 points x naught, y naught, z naught would serve as the input on the surface of Earth, and the so-called xyz is the point where you would try to convert the point for northing, easting, and up. So that will be converted to n, e, and u is the point, the vector to be transformed, where xyz is the vector to be transformed, and x naught, y naught, z naught is the position of the origin. Any doubt? If you having not a doubt, if you having confusion also, this is the high time that you should ask. Whatever silly confusion it may be, you can simply ask, because otherwise what is happening, when we discuss during viva these type of basic questions, your answers are not up to the mark of a PG student. So it is high time that you should avoid your confusion also. If you have any confusion, you can simply ask that, sir, why it is like this, why it is like that. We'll be happy to answer it out.
सर ये जो लेफ्ट हैंड सिस्टम बोला जाता है NEU को, ये किस बेसिस पे हम कहते हैं सर? मींस कि अगर हम लेफ्ट हैंड के फिंगर्स को अलाइन करें म्यूचुअली परपेंडिकुलर डायरेक्शंस में, तो ये उसमें के मतलब कि जो ये NEU सिस्टम है उसी के पैरेलल आ जाता है इस वजह से?
Okay, my network got stuck, so I'm just sharing it again. Okay, so I was asking is that if you have any confusion, not only doubt, if you have any confusion also, that you can ask right now.
Yes, sir.
Am
Sir,
I
I was
audible,
asking. Yes, sir.
Sumit?
Yes,
Am
sir.
I audible?
Yes, sir.
हाँ,
सर आई वाज
हाँ.
आस्किंग दैट कि जो ये लेफ्ट हैंड सिस्टम है सर, इसका ये कैसे मतलब हम इसको देखते हैं कि अगर हम लेफ्ट हैंड में तीन अपनी फिंगर्स को म्यूचुअली परपेंडिकुलर राइट डायरेक्शन ओपन करें तो ये तीनों डायरेक्शन में यानी नॉर्थ अप एंड ईस्ट डायरेक्शन में अलाइन हो जाए, क्या ये इसका सिग्निफिकेंस है?
Say again, what you are saying?
Sir, I was saying that this left hand system means is that when we use our left hand and align our three fingers along in mutually perpendicular direction, then these three fingers align with the direction of north, east, and up direction. Is that mean of
Yes,
left? Okay.
yes, 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 yes.
And sir, what does it mean by right hand system? Here we are not using like how we can use the right hand system in what way?
See, the right hand system and left hand system can only have a phase difference of 180-degree, or you could have the conversion from left hand system to right hand system will have only the role play with the z axis. Okay, you can convert from one hand system to one system by reflection, left hand to right hand system. Okay, that means you will have only put up the z will not change, only the value of one of the axes, x or y, would have a opposite sign that will be converted. Okay, so use of right-handed system is popular in the global coordinate system, and the left-handed system is used for the so-called the local system, which is topocentric system.
Sir, here what we are converting is that from left hand to right handed system. But sir, what we are seeing that x, y, and z axis that is only in left hand system means one thing is just opposite is x axis. Otherwise, all left z and y axis is aligning with the same thing. Sir, how this?
नहीं, अब देखो, अब नाउ अब आप इसको ऊपर पे देखो, ये है आपका NEU, ठीक है, इसका इसका आपको ओरिएंटेशन देखना है विद रिस्पेक्ट टू x, y एंड z, ठीक है।
Yes, sir.
तो अब आप ऑब्जर्व करिए कि u z के अलाइन कब होगा, जब आप उसे e के रिस्पेक्ट में मूव करेंगे। If you rotate with respect to E, then you will be aligned with Z. Okay.
Yes, sir.
And how this N will be aligned to X when you rotate with U.
Yes, sir.
Okay. So
Yes, sir.
translation looks okay because you are clearly looking at the shift between this point to this point, because this is the origin of this coordinate system and this is the origin of global coordinate system. So this translation looks okay, so that the system origin coincides. One reflection, so that left to right-handed system you go into the left hand to right-handed, and then two rotation. Two rotation means first rotation with respect to either start with U, and second rotation either with respect to E. So two rotation, sorry, not reflection, two rotation, and what will happen? Your complete NEU would be aligned to X, Y, and Z.
Okay.
Here we are using completely the matrices, but what will happen if you read from the book? They will tell you at what angle they are transforming those different N, U, and E for this X, Y, and Z. My question to you, all of you, is that don't look into this global coordinate system as suppose they are giving you X, Y, and Z. Okay, that's fine. It is X, Y, Z you are getting, or latitude, longitude, height you are getting. But for working on a local scale, when you have a local khasra map of a area, or maybe topographical map from Survey of India in your hand, you cannot control the two different values. On your map, you will be having local values. On your GCPs, you will be having global values. So what will happen? You have to convert your GCP to local values. How do you convert it? By this. You convert it by this. How you are converting it in your local field software? By selecting the UTM projection. Probably in the second or third lab, you will be having this conversion. That means you can select your how you want to represent the result on your screen. So receiver can give you XYZ also, receiver can give you latitude, longitude, height also, and receiver can give you northing, easting, and up also. What do we call this NEU? Is that local geodetic? What do we call it? Lambda phi, global geodetic, or simply geodetic? But what do we call it? NEU. It is local geodetic coordinate system. Why? Because again we are taking angles and distances in this system, NEU, where north, east, and up are defining the coordinate system. In the global system, your XYZ are defining the coordinate system, isn't it? And once more, that's why I'm telling you, this is not only the doubts, some confusion would also be there in students if they do not carefully watch that what we are doing here. At local level, not only local geodetic, you can also have local Cartesian coordinate system also. That means there would be X, Y, Z at local level, not like NEU. There would be different X, different Y, different Z. But that is not suggested in general practice. It is suggested in the general practice that you work with northing, easting, and up, so that you have a connection between global and local. See, these kind of things will not be written in any books. This is from our experiences that we are sharing, because such doubts are always there in our minds also when we were studying this subject. So what do you mean by local system? Why do you mean by global system? Why we are reading local again when we have a global system? If everything is in global, then what's the problem? The problem is when you get into the work, when you are in the study, you are very happy with the global. But when you get into the work, then there is a problem. The maps, which would, let's say you are working in, some of you are working in the Allahabad region, and many of the seniors are working in the Allahabad region, then you digitize the image. In that digitization, the process of digitization and georeferencing is done just to have the map coordinate converted to global coordinate. Otherwise, what will happen? You cannot work it out. So many challenges are there when you work with local scale and global scale. Anyways, we will see. Any questions? So we will start this figure of Earth concept in the next class. By the meantime, I'll share just now, because I forgot to share the few basic very few basic papers, so that you work and start reading certain content. Very two-page pamphlet I am sharing with you, so that they will develop your conceptual understanding, and you may think again. So that one I'm sharing, I don't know whether it is
Let me just share in your chat box. That would be much easier. Very basic paper. Very basic 2-page paper that I've shared. Just see whether it is reached to you or not. It is taking too much time. I don't know why, network issues or not. Let me share with the.
Let me just again share. अब देखिए आपको मिला होगा.
यस सर आ गया.
ये तो आपका अर्थ रोटेशन का एक पेपर और अच्छा है, बट अर्थ रोटेशन के समय हम उसको शेयर करेंगे. अभी तो सिर्फ रेफरेंस सिस्टम का आपको शेयर करना है.
सर आपने जो जीडीपी के टाइम पे 4 रेफरेंस करके कुछ शेयर किया था सर, वो भी हम लोग के पढ़ने को ठीक रहेगा ना?
4 रेफरेंस वाला क्या?
सर आपने जीडीपी वाले सर क्लास में शेयर किया था उसमें सर, लेट मी सी.
हाँ, ठीक. जीडीपी वाले में नहीं, लैब वाले कोर्स में.
हाँ सर, लैब में ही मतलब कि था.
आपको मिले तो इस पे भी जरा शेयर कर दीजिएगा.
ओके सर.
I'm sharing one. Actually, at this stage, what I'm trying to do is to give you very precise paper so that you do not get confused with too many things. Otherwise, what will happen? There are multiple papers which you can refer to at this stage, but again, that would be confusing, because your mind should filter out what is okay, what is not. I've shared a modern terrestrial reference system part 1. Part 2 is आई गेस अभी डिस्कशन करना है उस पे, उसके बाद ही आप लोग पढ़ पाएंगे उसे। पार्ट 3 भी अभी डिस्कस करना है, पार्ट 4 भी डिस्कस करना है। तो आपको मैं एक कोऑर्डिनेट एंड टाइम सिस्टम का एक पेपर ये दे रहा हूँ, ये आप पढ़ सकते हैं, मैं अभी शेयर कर रहा हूँ। तो जरूर एक बार पढ़ के फिर नेक्स्ट स्लाइड में I think it is taking too much time. So I'll share with the email, I guess.